Greetings, Chem 2 students. Mr. Keister here with you again. This is the video for Wednesday, September 3rd, 2020, which is actually our 24th day of school for the fall semester. Always keep in mind, though, that the dates could change for a variety of reasons, but lessons and the order of those lessons will remain the same regardless. So let's look at our do-nows and see what our schedule is for today. Today you're going to pick up Unit 2.2 review, all right? We must have a test coming soon. As a matter of fact, we do, which is page 42. It says save a spot for 41. It's coming tomorrow. That's the lab we have coming. From yesterday, we got a half-lives chart and our radioactive decay assignment, which we began yesterday and are going to finish up with that today. So your homework was numbers 1 through 3 only on the radioactive decay assignment. Hang on to that, of course. We're not done with it yet. But you can check your answers if you're here at school. They're posted there on the backboard. They were at 7 this morning. If you're at home, that answer key would also be posted in Canvas on my answer keys page by 7 a.m. this morning as well. So make sure you've done that correctly, the chart method. So we're going to finish up Unit 2.2 today on nuclear chemistry by learning how to do the logarithmic method of radioactive half-life. So get out your calculators. We're going to be using that log key, LOG, which is log base 10 key. We're going to be using that today. You're going to finish your homework assignment for tomorrow. And then, of course, I handed out the review today as well. So we will be having a test here coming up soon, okay? And I'll talk to you more about that tomorrow. So anyway, having said that, oh, and mastering, don't forget that. Our next online homework assignment in mastering, Unit 2.2 nuclear chemistry, again, is due this coming Friday, 2 days from now at 7:30 a.m. So don't forget that. All right, so let's look here at the board, and now we're going to do the logarithmic method. All right, it's a little longer, but a little more math intensive, of course. But very effective nonetheless. So here's the situation now. So yesterday, if we had a whole number of half-lives transpire based on time, or we had a decay that was a factor of 1/2 based on remaining and original masses, then we could use the chart method. If that's not the case, then we're going to have to do what we're going to do today. So if the number of half-lives involved is not a whole number, or if the mass reduction due to decay is not a fraction or percentage that is a multiple of 1/2, then we've got to use the logarithmic method. And here is the equation for that. T is equal to 3.32. That is a constant. All right, that's always going to be there. Times t to the 1/2 times the log, and this is LOG. You probably have 2 log keys on your calculator. One is LOG, that's base 10. That's the one we're using. The other one is ln, which is natural log, which is a function of e, if you've done that in math. We will not be using that one, all right? So we're using log base 10. Anyway, the log times the ratio of the original mass to the remaining mass. Again, t to the 1/2 is the half-life time of the radioisotope. That will be given in a certain time unit. T then, of course, would be in that same time unit. Again, remember the time units have to match. MO, of course, is the original mass of the sample, and MR is the mass of the remaining sample once decay has occurred. So let me move this screen up, and we will do a couple problems here. A little higher there. There we go. All right. So we have a sample of phosphorus 32 that has an initial mass of 50.0 grams. So that's our original mass, MO. Is placed on a lab shelf. How much of this isotope will remain? So we're looking for the remaining mass after 65 days. So that is the time that has passed. All right? So just to prove to ourselves, in fact, you would need to do this, that we can't chart this thing, let's use our little equation here. X equals t over t to the 1/2. And see if this is a whole number of half-lives. All right? So if we take our time, 65 days, and the half-life time for phosphorus 32, I'm looking it up on the chart here, is 14.3 days. So t to the 1/2 is 14.3 days. Again, those time units must match. So if we take 65 over 14.3, we get 4.5 half-lives, which means we cannot chart it. No can do. All right? It's not a whole number of half-lives. All right? So the charting method is out. So we're going to have to use the logarithmic method. So t equals 3.32 times t to the 1/2 times the log base 10 of the original mass over the remaining mass. So let's plug in what we got here. All right. So we know our time is 65 days. 3.32 is a constant, of course. We know our half-life time is 14.3 days. And the log of, let's see, we know our original mass, 50.0. We do not know our remaining mass. So we're trying to find that right there. Okay. All right. First things first. I want to isolate this log function over here, the log of 50.0 over mr. So the first thing I'm going to do is multiply 3.32 times 14.3 and divide that out of there. All right. So 3.32 times 14.3, 47.476. So we're going to divide both sides by 47.476, which will eliminate that entirely. Okay. And over here, we then get, we're not rounding yet, 1.369, 112.815. Now, this has gone away, so all we had over here now is the log of 50.0 over mr. Again, we want to isolate this log part of the equation over here by itself. All right? Now, here's what we got to do next. To get rid of this log function, we are going to inverse log. You take the log times the inverse log. For those of you that have had Algebra 2, hopefully have worked with this before. If you take the log times the inverse log, of course, anything times its multiplicative inverse is equal to 1. All right, so that's what we're going to do. So here's the thing now. If MO or MR, all right, either one is unknown. All right, need to inverse log. And if you look at your calculator, okay, so the log button is log. If you look above that, you'll see what the second function is, or the inverse function is, and it's usually called 10 to the x. All right, so this would be 10 to the x. That's the button we're going to want. We're going to 10 to the x both sides of the equation. Now let me explain that. All right, so let's do that. So I'm going to take the easy side first. If we inverse log, or 10 to the x the log, that's equal to 1. So the log goes away. So now all we're left with here is 50.0 over mr. Okay? Now we're going to inverse log, or 10 to the x this number. So what you'll do is you put this number in your calculator, 1.369, 112.815, and hit 10 to the x, which means you're probably going to have to hit your shift button or your second button in order to get to 10 to the x, which, like I said, is located above your log key. Now I'm going to show you my calculator. You may have a different one, but it's going to look the same. So anyway, as you can see, my log button, LOG, is right there. And up, see it right there? And up above it, it says 10 to the x. So in order for me to get to that, I've got to hit Shift log. That'll get me to 10 to the x. Let's see if I have another one here. So here's another common calculator that a lot of people have. Let's see. Again, here's my log button right there. It says log. See that right there? And again, here's my second button. It's blue on this one. And if you look above the log button, it says 10 to the x. So in other words, in order to get to that, I'm going to have to hit second log, and that'll get me to 10 to the x, and then I'll plug in the number that we have. Okay, so that's how you do it on your calculator. So if we 10 to the x, 1.369112815, we get 23, again, no rounding, 0.39444,868. So now we're down to an equation we can work with. The log is out, okay? So we have 23.39444,868 equals 50.0 over MR. I can just put this over 1, and now we have a proportion that we can cross multiply and divide. So I'll do that over here. So I have 50.0 times 1 equals 23.39444,868 times MR. So I'm going to divide both sides by 23.39444,868. And now we're going to get our answer. And it looks to me, we've got 3 sig figs there and 2 sig figs and 65. So we're going to round to 2 sig figs. And that comes out to 2.1 grams. And that would be our remaining mass. So just FYI, as a quick check, we said we underwent 4.5 half-lives. So 4 half-lives mean the mass to be cut in half 4 times, right? So if we start with 50 grams, we cut it in half once, it's 25, twice is 12.5, 3 times 6.25, 4th time 3.125. Well, we went more than that. We didn't go a 5th half-life, which would be like 1.16 or something like that. And we're at 2.1, so that makes sense, right? We went farther than 4 half-lives, but we didn't go to 5. So this makes sense. And again, without a whole number of half-lives, we wouldn't have been able to chart it and get an exact figure, all right, like we can here. All right, so let's look at the second one. We'll do that. Sample of cobalt-60, if I remember correctly, the half-life time for that is 5.26 years. I better look that up. Yep, that's right. It's used for cancer therapy. It has an initial mass of 25 grams. So there's our original mass. Stored on a lab shelf. How long will it take? So we're looking for T now, for the mass to be reduced to 6.50 grams. All right. So here again, can we chart this thing? Well, if we do our little equation, X equals MR over MO, we get 6.50 over 25.0, which is 0.26. 0.25 is a factor of 1/2. It's equivalent to 1/4. But 0.26, even though it's close, is not. All right? So we cannot chart this one. All right? It's not a factor of 1/2. It was close. Not close enough. All right? So we're going to have to do the chart method here. So again, T equals 3.32 times the half-life time times the log of, again, MO over MR. So let's see what we got here. We're actually solving for T, so that's still T, 3.32. Half-life time is 5.26 years, which means when we calculate T, it's also going to be in years, times the log of MO is 25.0 and MR is 6.50. Okay, now we got a little different situation here. All right, little different situation. I'll put a little note here. Since both MO and MR are known, all right, we're just log. In other words, we're just going to use the log button this time. We don't need 10 to the x or the inverse log. We're just going to use the log button like it says right here. Just log their quotient. All right? So there's no 10 to the x needed on this one. Makes it a little easier, actually. All right? So let's do that. So we have T equals 3.32, 5.26. Okay, so I'm going to do just what it says here. I'm going to find the quotient here, 25.0 divided by 6.50, which is 3.84, a bunch of decimal places. And now I'm going to hit the log button. Not 10 to the x, the log button. And there we go. And that number is, again, no rounding, 0.58, 502, 6652. All right? So you see, we don't have a proportion to set up and divide and all that business. We're just going to multiply these three numbers together, and we got it. So actually solving for time is a little bit less time consuming. No pun intended. All right. So I multiply those three numbers out, and as I look up here, we got 3 sig figs, 3 sig figs, and 3 sig figs. So we're going to round to 3 sig figs. We get 10.2 years. And again, it's in years because the half-life time is also in years. All right? So I've given you two examples of how to use the logarithmic method. One of them, if either MO or MR is unknown. We did that one before. And this one where MR and MO are both known. All right, are both known, and we're solving for time instead. So I think that will allow you to finish the assignment that we started yesterday. So make sure you do that. And then we're going to move forward. And we got a lab coming up here next in regards to decay and nuclear radiation. And then we got a test coming up. So again, you picked up your review today, so you also need to be working on that. So for Mr. Keister here again, I am signing off for today. Everybody stay safe, keep working hard, and I will catch you next time. So long, guys.